the moon. So please give a warm applause to Carsten and Robert.
Okay, hello everyone. As already said, I'm Robert Böhme, team leader of the part-time scientists, and this is my colleague Carsten Becker, leader of the electronic groups in our team. And today I want to show you a little bit about the struggles and achievements we had this year, and we got some cool topics coming up and some mind-blowing revelations in the end. So let's get started. First of all, the topic for this presentation is, if my presenter works, it works, is not your grandfather's mission to the moon. So today I want to show you some cool things that are not that ordinary on our way how we want to get to the moon. So just in very short, who are we? The part-time scientist is a group of about 100 scientists and engineers trying to do the first private mission to the moon. So this is very short because I think hopefully most of you know about it. Carsten will give you a short introduction.
Hi, good morning. How many of you actually have seen the other talks of us in the last, at the camp or at the Congress last year? Oh, that's quite a bit. So yeah, I will keep this very brief. So we want to get to the moon, and to get there we need to load our rover into a rocket. And this is from the rocket user guide that you can download on the internet for free if you want to.
So rockets actually have man pages.
Yeah, that's really cool. There's all the kind of a specification in there. And so what you can see there is the top where it says Spacehead Module. This is where the H-bomb was previously placed. This is an intercontinental missile that was used, oh no, it wasn't used, to nuke the USA. And so what they do is they take off the H-bomb part and put in our lander with the rover. And then the following happens. There is a silo that you can see, the lid is open, and then there you have liftoff. So this is pretty cool. This is pretty cool. You have, it looks quite nice because it's flying out and then it's standing there for like a second, and then it really kicks in. From a technical point of view, this is really, really challenging. You know, you have all kinds of vibrations, and the sound that you can hear, it's incredibly loud, and this noise is not so good for our electronics and everything that we have on board here again. I would like the part here, you can see the launch booster that is separated from the rocket before it actually starts. So this is step 1 was loading up the rover, step 2, launching it, and step 3 is obviously profit. So we will hopefully land on the moon and safely, and we will unload the rover, and then we will drive around, take some pictures, and do what nerds do, have fun. And yeah, what this picture here means is something we will explain a bit later in our presentation. But yeah, now Robert will present what we have done on the mechanics part.
So let's come to the very first topic where we talk about some technical and interesting stuff that happened this year. So mechanics, in our case, for extraplanetary use only. And one thing we've had is an interesting conclusion. It's that gravity always matters. So what does this mean? This means something like, if you can see on this picture, some people of you who have seen these images, maybe we didn't publish this one for a very specific reason. So some of you have visited us at the ILA in 2010, and if you notice, there is this little hill of little rocks down below the rover. There's a reason for this hill, and it's not just to look better, which actually most people thought it would. The reason is that the first revision of this R2 rover was built with 1/6 of gravity in mind for the lunar surface. So we sat there with our CHD software and designed a rover that could work on the moon. The problem is we actually want to drive it on Earth. So there's a little bit difference in gravity, and this led to a rover that has some problems with getting the weight balanced. So for example, you see these wings that connect the wheel part with the body part. These are actually made out of so-called FDM. It's a little bit like plastic, and it's not strong enough to withstand the gravitational forces. So the rover would actually, in this image, would actually sit on the ground. And the same goes for all the suspension parts that are in the wheels. So we actually had to modify the system to get it in a driving state. And this is probably how you've ever saw our 2 rover. This is probably how you know it. Then this is the series where we've replaced it with metal part. These metal parts obviously had the problem that due to the fact that they're out of metal, they're a little bit too thick, and so we couldn't get the cables in there. So one thing we've learned is that we need to take into account the effect that we need to build a rover that can both work on down on Earth and actually can both operate it on the moon. So we've come up with a completely new design, and we will show you a little bit more about it in the end. But this is actually something that accomplished both goals. One other story, it's very interesting, is about glue. So sometimes in mechanics, you're not just using screws or other things to make things stick where they belong to. Sometimes you just need some special glue, for example, on screws to protect them. And there's an interesting situation when you come into the room and you see an engineer standing there, in one hand, one bottle of glue that is made for space use, so it's really strong glue, and the other hand, it's just industrial glue. So and then he's just standing there and is thinking about, oh my God, which bottle did I just use to fixate this wheel onto the driving shaft? And yeah, then he realized he just used the wrong bottle, which is a big problem, because in this case, we actually had one wheel that was glued with the wrong glue, and yeah, we needed exactly this wheel to get off again. So it always happens this way. And we were lucky that we get it off. We actually had a good timing. But the problem, why is it so complicated to get such things fixed again? The problem with this glue, for example, is that they have a specific temperature where you could get them, let's say, get them off again. So, and the specific temperature for this industrial glue is at a level that you can apply to all these components without damaging everything that's surrounding it. So you have to heat up a very tiny spot on the rover to just get this screw again, loose again. The problem is with the space-certified glue, you can't reach this temperature without melting everything around it.
And let's not talk about the price of the bottle.
Oh yeah, that was another problem. Yeah, it's a little bit more expensive than the other glue bottle. But they pretty much look the same, that's the problem.
We should have used what we always use, hot glue or duct tape.
Oh no. Okay, so let's get to software development. Carsten.
Yeah. In the last year, we were concerned with the topic of actually driving our rovers around. You may notice that we have like 4 wheels that are steerable independently, and we have to find people that can actually drive it comfortably at best. And so the first model that you can think of how you could drive our rover with 4 wheels is like a car. But if you look at the equation on how the speeds are computed and how the angles are set up, you will find that this is a really nasty model. If you're bored, you can Google Einspurmodell, and you will find that there's tons of mass there, and it really is awful because you have some slippage on the rear wheel. This is not a good model. So the more obvious one is then to use what is used in front loaders. You know, those big vehicles where you can steer the front and the right and the rear wheels. It's a bit something most people don't think of is that you have different angles for the wheels because the diameter of the circle on the outside is bigger than on the inside, so you have higher speed on the outside wheels as well. And while this might actually work quite well, you have to consider that if you move the point closer to the center of the vehicle, the equations get a bit messed up and you need to fix a lot of cases. Also, you can't drive directional, like you set up the solar panel in a certain direction and you just want to keep the solar panel focused on the sun and move into any direction anyway. So while this model is easy and most people can use it for driving around, it's not taking full flexibility of what we have. And so we came up with a really nifty algorithm for steering that, and I want to explain it a little bit. So think of 2 vectors. One vector is giving a direction and a speed, and the other one is a rotational vector around the center of the rover. So what you can do with that one is that you can drive like this if you don't have any rotational vector, or you can rotate on the place if you're just using the rotational vector, or, and this is a little bit difficult to imagine, but you can drive into any direction and rotate at the same time. But this is a really cool feature because it takes full advantage of the wheel configurations that we have. But you have to do some trickery to get it to the 4 wheels. This is really straightforward to implement if all you have is a ball and you actually just want to roll around in a hamster cage on the moon. But we want to drive like real people, and so we have to implement it for 4 wheels. Okay, obviously you just translate the directional vector and the speed vector. This is quite easy. For the rotational vector, you just have to consider a bit a large circle, and then you will get those directional vectors that are perpendicular to the shortest line to the center. And as you can see, this depends on the geometry of the vehicle, but in the end you have a model like this. And all you got to do now is you just have to add those 2 vectors, and you can see that the blue vectors are the resulting vectors, which are the length is indicating the speed and also the direction of the wheel. So, anyone understand how this might work? Is it a little bit early for mathematics, or is it okay? Okay, so now we have this really nice model, but we have to enter a rotational vector, and we have to enter the directional vector. Directional vector on a 2D surface, straightforward, you know, distance to the center and the direction in a circle. But for the rotational vector, we didn't find a good input device until we found those ones. Those are really cool things. If you want to think around a bit with those have 6 dimensions of freedom, so you can tilt them in any direction, and it's really, yeah, it's a space navigator from 3D Connection. It's a really cool device. And so what you can do here is you can enter a rotational vector and the directional vector, and then you can take full flexibility of the rover that we have. I want to give you a little video of how we have done that. The good thing is that most people kind of get it, what you have to do here. And we have lots of fun driving around with that. Yeah, we will show you a little bit more of that later.
I think the actual interesting thing is that the younger the people are, the easier they can use this to steer the rover.
Yeah, old people suck at steering. No, I didn't say that. Okay, I have a little story to that one. So, what we did is in the last presentation we showed you the R0 rover, which is our software development rover, a little tiny metal version of it, and we wanted to use it to educate kids about the moon and stuff. So we developed an Android remote, and actually this one has kind of the loader configuration of driving, and this is really easy for kids to understand, to drive around. But at the one time, you know, sometimes when you see, I got used to see kids steering our rovers intuitively on the Android remote, but when I saw an 80-year-old granny, you know, like, oh, cool, driving it with that was really fun. And yeah, the other thing we did have some fun with testing. One of the things we have to consider is that you have a 3-second delay when steering the rover on the moon. And this is really tough testing, I have to tell you. It's no fun at all, except for the drinking part. And yeah, we will show you a little bit more of that later as well. But now Robert is going to talk about software. Didn't I talk about software as well?
I think so. Anyway, everyone can talk about software, so it's a free land, everyone. So yeah, that's actually interesting picture. So we got a rover class, which I found is interesting, to just put a rover into a header file. Anyway, our software is not year 2K compliant, just have to note this. So what can we say about software that is interesting and that's happened this year? I picked one topic, which comes down to simulations. So when you want to get to other planets, then I think it's interesting to get as much as information than you can about this other planet up front before actually landing somewhere over there. So this is what we did. We've teamed up with the guys from the TU Berlin and also from the DLR to get access to the raw material that the Lunar Reconnaissance Orbiter that is consistently surrounding the moon and taking pictures to get these data processed and putting it into the simulated model. So we've come up with a simulation engine and tried to import all these raw data, which is a little bit more complex than you might think. I actually just downloaded the raw files and tried to get a view of it, and I totally failed at it. So luckily, some other people are more skilled than I am in regards of software. So we've built the simulation engine, and this was the very first time when we've loaded the simulation data, and yeah, it's definitely something, but it's not the lunar surface, and it's definitely not correct. So what happened here is that we've had a model which has the so-called normals completely wrong. So everything is a little bit like flat surfaces across flat surfaces with no real height and depth, etc. So we tried to find out what the problem was. Then we've noticed that the interpretation of the data was the problem by itself. So then we adjusted this a little bit, so we got more height details. Then we realized, okay, we need more information, more details from the material that we have. So we need to calculate multiple images to get a 3D model. This was actually a stage that we had for quite a long time. So on models like these, for example, are we using for not just to get information, but specific information. So if you have a physical model of the lunar surface, then you can, for example, look at the heights and slopes of certain hills. Then you can think about things like the sun angle while driving around. And there's a lot of other interesting things like communication vectors. So right now, our simulation level looks like this. So I think every one of you knows that the moon is not green and yellow. So I think if you can come up with a pretty good idea what these colors mean by the end, we have a question round at the end, then we'll definitely get some cool surprise. Because I won't spoil it, because there's some cool article coming up. And the hint I can give you is, if you look over here, you see some bright green dot. That is actually the place where, for example, our lander could be placed on the surface on the moon. So now the question is, what is this green part, and why is this other area yellow, getting away from the lander? So originally, without any informational overlay, the model of the lunar surface should look like this, for example. Hopefully a little bit more detailed, depending on the level of simulation you put in. Okay, so now we're coming to electronics and failures. I think it's a suitable topic for Carsten.
Oh, no. No, everything works out of the box when we do stuff.
Of course, plug and play.
Yeah, totally, yeah. So with the new rover, we had a new wheel configuration, and I will show you a little bit. So this is the wheel as it's spinning, and it can turn as well, obviously, because we want to drive into different directions. So the thing is, we use the same motors for driving as well as turning. And I can tell you that if you do not have a mechanical hardware limitation in how much the wheel can actually turn, it will turn infinitely, you know. And you have seen earlier, you have seen the wishbones that are that we used for to fix the new wheels, and they have the cables in there. And I could tell you that if we had used those, we didn't use those, then we would have cut more than one cable by, you know, turning infinitely.
And not just the cables.
Yeah. But making those wheels spin is quite a challenge, and so we developed a toolkit from MATLAB Simulink that connects to our QNX target, where we have the controllers running that are keeping the wheels spinning at the correct speed, so they can actually keep the speed even if you are climbing up a terrain, or keep a position even if there are some forces pushing against the wheels. But sometimes, as I said, you know, it doesn't work the way that we thought it should. And yeah, the problem we figured out is the following. You know those friends of ours, the ribbon cable, you know? We think it's a good friend, but you know, sometimes it's a beast. And this is caused by EMI, electromagnetic interference. So we had this I/O expansion header, expansion board, and it's connected with SPI. And so there's a clock on there, and there's the data, and you know, if we crank it up, the speed of the bus, and it worked quite okay. But if you added the motors, which are, you know, good antennas, you always think it's hard to make a good antenna, but actually sometimes it's too easy. So we had interference there, and the data transmission didn't work the way it was. We expected it to work. So we thought, hey, you know, Ethernet cables are shielded, so let's make an adapter from ribbon cable to Ethernet jack, and then we could just use the Ethernet cable. This is a really good idea, by the way. And instead of, you know, just relying on hot glue and something, we made a more nice-looking PCB, and this worked really well. That is, until we actually had the rover in front of us, and we saw the box where it had to fit in, because the cable is quite long and quite stiff as well. So we had to make another clutch, and yeah, this is what we got, you know. We went back to the ribbon cable, our good friend, and we interwove it with a cable, and we connected that cable to ground. And to our surprise, this worked really well. And yeah, if it would not be for our design ethics that we think this is really ugly, yeah, this is what we are going to use now, because it looks more solid. It has an Ethernet cable directly connected to it, and yeah, it's a nice looking PCB, and it fits into the rover. So we talked a lot about rovers, and most of you already have seen a few of those. But for those that haven't seen one, we will just give a short video that we made about how we are building the rovers. For those at the 2063, you will probably recognize this video. This is how we built the R1.
R1 over, yeah, it's written over there. You just.
Oh yeah, yeah. Cool. Yeah. You may recognize the Flintstones wheels we had on the last version of the R0 rover, and you probably remember this one. And it's not all fun, you know. It's really tough testing, you know, to know how it looks on the slow motion camera if you bump into a wall, or put a rocket on it, or transfer muffins from one room to another. This is all important data for our mission.
I think it's no fun for the rovers. Let's not talk about the drivers.
No muffin was harmed during the filming of this movie. It was delicious. But back to testing the driving. You know, it may seem really easy to do it, you know, but you see how he bumps into the bottles and stuff, and this is because the only way you can drive is, you know, like you give it command, and then you wait 3 seconds until you see what you have done, and most of the time, as in this case, it was that you bumped into a bottle, which is no good, because there are no bottles on the moon. It would be a rock. And this is some of the outreach that we did. This is a really nice moon playground that we built. And so the students can, or pupils can drive around it, and if you drive over a point, you will get some information about that point on the moon on your Android remote.
Yeah, we had some infrared beacons implemented into the, woven into the surface.
Yeah, not bacon.
Not bacon, definitely.
You may have an idea what this goes to, in which direction it goes. We do not know what's under this black tissue, but we probably will reveal it to you somewhere later. But now Robert is going to talk about what we are going to do in the next year.
At least some of it. Thanks. And yeah, 2012. So actually, one of the cool things we had this year, it's still this year a little bit, at least for some short time, is that we actually had our very first full-time scientist. And one cool thing about next year is that we will have our very first intern, which is totally cool. So, and one thing that we have on the roadmap for 2012, which is quite interesting, is so-called radiation testing. So that is something that we want to do pretty early. And so we are trying to find out how radiation influences certain parts of our electronics, like image sensors and other things. And on the other hand, we want to do some extensive drive testings with our new robotic platform. And of course, we want to do some camera testings as well. Yeah. And?
Have fun?
Yeah, that's of course, always. No, and just continue what needs to be done to get to the moon by the end of 2013. Still. So, I just want to take the chance to thank some of the people that helped us get to this point over the last 2 years. So one thing that is a little bit new is that we've entered into a cooperation with the DLR. I think this was after last, no, it was actually, we have actually announced it last year at the CCC. So we're working with the German Aerospace Agency, Deutsche Zentrum für Luft- und Raumfahrt, and some of the institutes and building the robotic parts of our rovers. So they're pretty cool guys, and yeah. Also, we're working with the TU Berlin, and the TU Berlin, for example, comes into play when it comes to these lunar materials, so the lunar surface maps, everything that's surrounding like DTM, so-called detailed terrain maps. Every time you say, okay, I really need a high-resolution map of a certain area, or I need to find out where would be a cool place to put my rover on the moon, because this is a question that you can't really answer, so can't really easily answer. So you have to take into account many things like how many stones are distributed across a certain area, and are the stones bigger than your rover or smaller? Smaller is better. And this is, for example, where the TU Berlin helps us. And of course, the TU Hamburg-Harburg, which helps us a lot in the electronic fields. I think Carsten can tell a story about this. And one other thing is, we are lucky that we have found a lot of partners and sponsors who helped us with supplying us with certain technology licenses and everything we need to get where we've got so far. And I think if you have something in mind with how it looked like last year, then we have 4 new additions on this map. For once, we have NVIDIA, where we're doing a lot of things with, let's say, really intensive data center computing, because these guys can really crunch some numbers. And also, we have our law firm SZA on the list. And of course, CMOSIS, which are the guys supplying the image sensors. Want to?
Yeah, the image sensors, they are used for on the moon, and they are known for building sensors that can sustain the harsh environment there. Also, they make pretty pictures. And then we have QNX, which is our operating system that we are going to put on the rover and will fly to the moon. It's a real-time operating system and quite nice.
Yeah, we had a presentation about this on the Linux Tage last year with our colleague Arne. And yeah, it's one of the few things, because many people ask us, why do you using an operating system like QNX and not Linux or some real-time Linux system? And we had a very long discussion about this afterwards, which was very interesting. So, yeah. So much for the 2012 part. Now I want to get to the questions part, because I think we can talk about a lot of interesting things, and I just want to get into the questions area. Before we start with this, if we want to follow us, just look up us on Twitter or Facebook. Yeah, the evil one is the one below. So it's not like in Futurama, it's not like we're following you, but just not on Twitter. So, okay, so as I said before, if somebody of you has questions, we will give away some very nice presents to the one with the best question, and as I'm a pretty bad judge, I will leave this to Carsten, who is always good at judging people. Let's find out.
So if you have any questions, the microphone is in the back aisle, so please line up there.
Hello.
Will you be able to get more rockets later and do this experiment again so that we can have an incremental?
Yeah, that's a very important topic. So the question was, will we be able to get more rockets later on? So as we talked about, the rocket that we just showed you was an old intercontinental rocket. There's still a whole stock of these lying around somewhere in some areas. So the point is that these are actually being disarmed, so they are no longer used for distributing nuclear warheads anywhere. So the point is that there is still a defined number, but you're totally right, they're not being renewed. It's a good thing in any way, but the reason is why everybody tries to use these is because they're quite, let's put it this way, they're very reliable, and they have a quite good, interesting price tag. But the point is, there's, for example, companies like SpaceX and the so-called new space sector. So SpaceX, I think some of you may heard it. This is a company who's on the private sector, who is doing the ISS supplies. I think starting also, I think they're already, no, they're starting.
No, not yet.
They're starting next year, early next year. So there's actually a private company doing what NASA and other companies did, not companies, agencies did before, in supplying the ISS. So there's actually a following up technical lead.
The problem is getting the money for going to the moon, because it's not something that every Joe can afford yet.
The problem is always the launch vehicle, and yeah, I think it's a good thing that we will have some new entities available in the near future. Yeah. I think if you attended the very first presentation that we had at the 2063, there we talked a lot about SpaceX, and back then SpaceX wanted to do a lot of things, for example, supplying rockets that we could use for our mission, but actually they really just focused on supplying the ISS because it was the near-term goal, and trying to do too many things can be a little bit of a problem, especially when building rockets.
Hi, how do you slow down from translunar orbit speeds to the ground, to the lunar ground? I mean, you show the departure from Earth and the rover bits. Who's in charge of the slowing down? How do you do it?
I'm just thinking about the right word. I just only know it in German. Not, the lunar. For example, if we want to land on the moon, that's definitely not as easy as landing on Mars, because, for example, planets like Mars have an atmosphere, so you can easily, not easily, but you can break down and then you can land. What's it? The English word for Fallschirm.
Parachute.
Parachute. Thanks. It was that easy. So sorry. So, for example, on such planets you can use parachute. That is definitely something that you can't do on a planet which has no air and no atmosphere. So, for the moon, you definitely need a chemical engine that needs to get you down from the orbit to the lunar surface. So it's not that easy that you say, okay, I have an engine and then I lower it, and at some point I'm just standing over there. So it really is, you have how to describe it, you have an entry that goes a little bit, if your planet is like this, then your entry goes a little bit like this and gets more and more sidewards down to the surface. And at some point, you will have to turn off these engines, and then you have a so-called soft landing, which means getting there, the part that you are currently above the surface, down to the surface without braking.
But there's also the boogie-woogie version of landing on the moon. This is what Jack, our trajectory calculation guy, said, is The way is you basically fly into the orbit of the moon where it's surrounding the Earth, and you just wait on a certain place until the moon comes by and you land on it. Also, you can use parachutes, but the problem is you will just deep impact, which is not very helpful.
Sometimes people actually do want to do impactor missions. NASA did it by purpose.
Yeah.
So, okay.
You're actually using quite a few custom parts you've built together. What's the outlook? Is it really useful in space as well as, you know, you're trying it here on Earth, but what's the possibility to use it on Moon, for example?
Okay, just let me first answer. So, custom parts is a little bit broad term, but for example, if you get it down to the electronics level, just as an example, then yes, it's right. We're actually using some parts that are not being used. Okay, most of the parts we're using are available for space, which is actually a good thing, but there are some parts that are not available for space. So there's a lot of things you can do about this, and there's a lot of things you have to do about this. It's so-called up-qualifying. So getting these parts, either replacing them with parts that can withstand this environment, or making these parts withstand this requirements. So then you have to look at your mission requirements. Our basic requirement for our mission is to have an operation on the surface time for about 1 month, which is 1 lunar day and 1 lunar night. So that is a quite tough requirement because of from plus to minus 160 degree temperature shift, which is quite a lot. So
yeah, except it's 120 and one is 180.
Yeah, 120, but it's the
details, you know.
Anyway, so the point is, right now we have a lot of technology that is space certified, that is really expensive and got a lot of documentation attached to it. Documentation is a whole building full of paperwork just for one screw, for example. So, which says that this screw is safe to use in this, and a long list of other constellations. And it costs actually much more to do this documentation than to just build this screw or change it to another one. So, I think it's very important to use custom parts and get custom parts to be qualified to get the costs down of this mission.
Yeah, but there is no change in physics. You know, a screw will work the same way on the Earth as it will on the Moon, except for the oil part stuff.
Yeah, of course.
What is Schmiermittel? Ah, you know what I mean.
Yeah, so there's really a lot of things you have to watch out. Just to name a few, you have the regolith that gets into every part and is a very sharp, tiny particles that work on all the mechanical parts. Then you have the radiation, which is a very strong problem for all the electronics. So you couldn't, normally people always like to do some things like CubeSats and TubeSats, where they can use Android hardware, like I think the things that you find in a smartphone, and just shoot it in the upper Earth atmosphere and let it fly there for some time till it burns. So the point is that over there, the radiation is not as hazardous as it is on the lunar surface because the moon really has no atmosphere at all, and over there you still have some protection by Earth. I think you have a pretty strong one still.
Yep.
So that's one of the reasons why you can actually use this hardware that you can buy everywhere. But on the lunar surface, you really have to find some ways to get your hardware protected.
Yeah, the low Earth orbit is the baby swimming pool of the space environment.
You showed a rover with 4 wheels. Do you ever think about maybe more or less wheels or chains on the rover?
Of course. I think we should spend quite a great deal of time just thinking about how to actually do things. If you look at the average moon rover or exoplanetary rover, let's put it this way, then you have something like, I would say, 6 to 8 wheels. Yeah. 6, yeah. So most of them, sometimes you have like 2 wheels paired at the backside with the other 2 wheels at the opposite side. So there's a lot of different ways to do this wheel system, but they're all limited in their degree of freedom. So, and I can't really give an answer why everybody is just doing 6 and 8 wheels. There are very good reasons for this, but our reason to do 4-wheel configuration is to want to have the greatest degree of flexibility and freedom for movement.
Yeah, and chains are a really bad idea because you have many parts that are working, and So the regolith will move into those moving parts and will destroy it really quickly. So it's not like a good idea to use chains.
Another thing is the energy requirement, because the biggest constraints that you have on the lunar surface is your energy level. So one thing that people always think about is, hey, let's build a bigger moon rover, let's build a bigger lander, or let's build the smallest moon rover ever. But people always forget about the simplest thing, energy. Because there is no power supply or wall plug somewhere on the lunar surface, at least not as I know about it. If you find one, just let us know. Anyway, the point is that it all is defined by the power level. So you really have to design your rover that's from your power source down. So if you know that your solar panel needs to have a certain size, then everything has to be designed around this parameter. Because if you don't have enough energy to drive around, then you don't need a rover on the lunar surface.
Yeah, so one addition to the power thing. So you have, you may have seen the rover on a 26C3 and on the 27C3, and you will notice that there is a difference in size. And if you have a good memory, then you might notice that this one over there, the big beast, is a little bit bigger than the previous version. And mostly this is caused by power issues. We noticed that we need more energy than we initially thought. And so we increased the size. We increased the size of the solar panel. And yeah, because it's tiltable, we can adjust it to the sun. And if we just have 6 wheels, we would skid steer and would turn the solar panel away from the sun. So this maybe answer your question as well.
Yeah, that's another reason why we choose 4 wheels, right?
Hi. So first of all, thank you for the presentation. It was great, I thought. It seems you're focusing on the rover. So I was wondering, are you contracting the transfer out, or are you designing that as well, or how to get to the moon?
How to get to the moon.
Are you doing this yourself, or are you buying this somewhere, the service?
It's a little bit of everything. So you can't build engine parts. Okay, actually, I have to correct myself because we have one team member who does this, but you can't actually. Okay, we say as a team we can't actually build engine parts that get us to the moon ourselves. So that's definitely for sure. So you have to contract with companies who can do this, and yeah, I think that building this so-called lander, which is the transfer module, is something that we're currently doing in broad cooperation with a lot of companies, entities, universities. So there's a lot of people involved from a lot of different areas. So, and I think this is the only way it can work. Because one limitation that you have is you have these so-called deliver times. I think that's the right term. So, for example, you need some parts, and especially when it comes to the lander, there are parts along it which can take delivery time like +2 years, for example, which is a problem, definitely. We want to get to the moon in time.
Okay, so have you started on this, or?
Yeah, of course. I think we showed some of our lander development at the last 2 congresses. Yeah,
all right.
Definitely.
Thank you.
So, and yeah, I just was thinking about if we did some other presentation on this, but
yeah, it's not just the problem is it's a very complex structure, and it's not. You cannot lift it onto the stage easily, and it cannot drive around. If you would start it here, you would.
The problem is that you have it in a computer, and you can do a lot of simulations, but for people to show it, it can't do anything fancy. So the rover can drive, but the lander can only fire up its engines, which is something that you can't do in here. And if you do it in a simulation, then it only looks cheaper than Avatar or Toy Story. So. Okay, thanks.
Any more questions?
By the way, you wanted to give...
Yeah, wait, I wanted to say that. Yeah. Those people that have asked questions, please come to the front and you will get your shiny whatever from Robert.
Oh, I'm the guy who can give presents. Great.
Yeah.
So, yeah.
So that's...
Any more questions if we say what cool stuff we have? For example, I know it's like children. We have Google laptop cases. I think they're pretty cool. So anyway. Or is Google too evil? I have no idea. I'm currently not on the watch list. I only noticed that Facebook is currently evil, but it's always changing too fast.
Yeah. Oh. One more? No.
No, there's a question from the internet. Actually, I have a question. Is this question good enough to get one of the Google thingies?
So you're asking as a signal angel, or you're asking for the internet?
No, I'm asking for myself.
Okay, maybe you get.
I think that actually qualifies, definitely.
Yeah.
So, yeah.
Good.
Okay, just one thing I thought about the four-wheel problem and just widely thinking about it, and I think maybe because there is less gravity out there, maybe it's you have better friction if you have 6 or 8 wheels. I'm not sure, maybe you have to think about it. And another problem would be if you lose touch with ground. I mean, you're in the outer space, you have those 3 seconds delay, and if 1 or 2 wheels are in the air, let's say in the air, I'm not sure if you're able to control your vehicle anymore. So the last idea I had, maybe because why they use 6 or 8 wheels, is if you have a failure. I mean, you're in outer space, it's very cold, one wheel gets stuck or doesn't work anymore. So if you have only 4 wheels, 3 wheels left, I'm not sure if you will be able to steer around with your vehicle anymore. So with 6 or 8 wheels, might be still possible. So just wild guesses why there could be better to have 6 or 8 wheels.
Yeah. There is also something that we didn't talk about specifically, but we can adjust the height of the wheels so that, for example, if we are in a slope, then we can still have the rover, sit straight because we can adjust the height of the wheels. So this gives us a lot of flexibility regarding the terrain that we can travel to. And also, you can argue that if you have 4 wheels, you have less points of failure than if you have 6 wheels. So, you can argue it around, and we found that 4 wheels are actually working quite well for us.
Yeah, I think it's a good idea to just keep everything as simple as possible. That's what I always try to do, because people in our team always come up with, hey, Robert, I got a great idea, let's just do this. And sometimes if you talk about it, then you just notice, okay, we just have to do a different mission, just if we just want to do this. So, keeping things simple is very important.
I just wonder about the size of the wheels. So I don't know how it looks on the moon. And but if there's a stone of the size of one of the wheels, so it's quite difficult, I think, to
Does this help to answer your question a little bit?
No, I just wonder, is it really possible with such small wheels to really drive around on the moon? Because I think if there's like a stone or something like that, you can't go past it. Like if if you have a car, you have like a wheel like this, and it's possible to drive over a stone, but it's...
Yes, I can answer this question, I can help a little bit with it. That is one of the reasons why we've got to the subject of simulations. So having wheels like the wheels we are using is a limitation. So you can't land, for example, on the one of the south pole area around it, because it's a very cliffed area. So we have a very rough terrain, and the wheels wouldn't definitely be able to travel somewhere. At least the rover couldn't get away in any place. So that is one of the reasons why we've been doing these simulations and looking at these maps to find an area which is actually pretty large and has the right kind of lunar regolith density and the right stone distribution, and how to put it. So if you have rocks on the surface, and so we were just watching out that we're not having an area where we have only very big rocks which are so intense that we couldn't drive any straight line, for example. So the area where we're actually landing is suitable for the wheels that we are using. Which is a cool thing. Think about this, because you're landing on a different planet, but you already have the possibility to put you down onto the surface and look around how it would look like if you're actually on the surface. It's a cool thing, actually even before getting there.
So do you also have some limitations where you can actually land with your rover? So depending on the transfer, so can you choose any point and they can drop you off at this point, or are there also some limitations?
There are no limitations in physical terms of view, but there are limitations that kind of make sense. For example, the North Pole and the South Pole, they are known for being very rough terrain with big craters where you have high slopes. So that doesn't make too much sense to land there. Also, landing near an Apollo site is really cool because you can take pictures of the Apollo landing site. So even that would be a reason alone to just land there, to see if there is really a flag, and and touch it and see if it's waving. Like,
I think if you touch it, then you can never travel to the US again.
Who wants to go there anyway? Yeah, so this makes sense, and also because the landing sites are very well documented with pictures and everything, it also makes sense to go there because the pictures taken from the surface itself and described by the astronauts are the best information you can have about the surface, even with the Lunar Reconnaissance Orbiter taking really high quality pictures. Yeah, so you can set yourself a challenge and land wherever you want, or you can do it the simple way. So we prefer the simple way.
So the internet wants to know, is it all C or C++ you're using for programming?
Yes and no. Yeah, sure, we are using C for developing the software that is running on the rover. But because we are having an FPGA, we have to develop the hardware with the language known as VHDL. That is really ugly. Yeah, so we are using VHDL, C, C++, and for the Android remote, obviously Java. So we are using the tasks, the tools that are the most straightforward for implementing, for getting a problem solved. Okay. No religion involved.
And the internet wants to see the rover and want to see it driving.
Yeah.
I think we can help with this.
If this is a question asked from the internet, the answer is currently no.
Ah, that's right. I think because but everyone in the audience definitely will have the luxury. But we will have some pretty cool material on this in January, so just have to watch out. And I can name the place where you watch out. If you are on Facebook and if it's not too evil for you, then you can just type into the search field, hell yeah, it's rocket science.
Yeah.
Yeah. And then you will land on a pretty cool page, hopefully. I think I've seen two people with questions.
Yeah, you said you want to stay a full whole day on Lunar. With day and night, how do you get your energy during the night? I mean, did you have any big batteries or something, full cells?
Yeah, it's very easy. We don't. So we do not have any energy during the night because we have a solar panel and we have very small batteries compared to what you would need to sustain the night. So it's kind of like if you switch off the lights, then the rover is hibernating, and then the sun goes up, and then we are hoping that we can receive a beep back from the rover. And if everything works really, really well, we can actually drive again. But you know, with the temperatures of minus 180 degrees, this is nothing that we want to guarantee. I mean, do we make any guarantees?
No, not at all. Yeah. But it's actually one of our technical goals, at least to try it, to take with us a battery combination that it's not enough to power the rover at night, but to keep it alive. It's just a try. So, and it's a good thing about this entire mission, we're trying out a lot of cool new technology. New technology, maybe not in the fields of industry, but in aerospace, definitely. I think there was one other question, but the guy just simply went away.
You want to see rover? Ah, one more question. Ah, sorry, one more question.
Oh.
Sorry, what?
I just was wondering where your rocket is actually from, because is it an American missile or?
With an H?
Just give me a second, and then you can look at the video and you can pretty much figure. Ah, there it is. Just, sorry.
Yeah, no one knows this logo.
Ah, sorry, this video starts, okay, video starts automatically. That's too easy for me, sorry.
Yeah.
Yeah, you don't know the logo, but does this look like an American launch? It's not Cape Canaveral, it's a little bit like Roscosmos, so it's a little bit more like in Russia.
Okay.
That's actually the guys who made a pretty cool thing for Christmas Eve, especially for Germany. So I think if some of you noticed it, we had these very bright, how's it called, line of light, and it's like a Lichtschweif, I forgot the word. I posted it on Facebook and I forgot the word, sorry. But anyway, we had this pretty bright light on Christmas, which was the upper part of Soyuz rocket, which was burning in the atmosphere, which was pretty cool, quite on Christmas Eve.
Here, there was a question about what the
color is about. Okay, so somebody has an idea. Ah, you got a perfect slide. So with profit written on it. Okay, so does somebody has an idea what this coloring means? So, just shoot.
Is it kind of a potential, like robo-friendly area?
Yeah, somewhat. That's almost the right direction, yes?
Flatness. What? Flatness?
No.
Yeah, no, not.
No, not really. But it has to do with it. It is. No, I think that would look a little bit different, because I can guess that there will be a lot of stones over here.
It's not the distribution of stone size.
Sun angel could be, but I think would say that the angel would be normally a little bit wider. Ah, there's a hand over there.
We would love to have the information about how soft the surface is at certain points. This would make it life so much easier.
I think this is not something easy that you could calculate.
The edge angle? Or
slope angle? No.
I think it's a little bit too complex.
Yeah, but I was surprised. I was guessing that, but
that somebody,
probably
I think this Congress perfectly fits the topic about what this map is about. So
it's too early in the morning.
Anyway,
yeah.
So do you want to say it? Yeah.
Yeah. No.
Okay.
I don't know what it is. You know.
You don't know what it is? It's a map. But anyway, what it is about is this simulation shows you, for example, if you take this point and say this is my lunar lander, then what we've did with the simulation model is finding out if you use your lander as a communication relay and you want to communicate from your lander to your rover, then you have the regolith in between. So, and the regolith itself is pretty good at blocking communications. So, and what we've been mapping out here is the area with good communications for our rovers and the area with worse communications. There are also areas where you have totally non-communication. It's not that easy. It's not like, hey, there's a mountain and after the hit behind the mountain there's no communication. There's a quite interesting mathematics involved in it. It's the so-called Fresnel zone. And it's about the mass that is in between you and the point where you want to communicate with. So we are actually doing this physical model, taking into account the height of the rover and the possible height and position of the lander, and mapping out the area where you have some good communications with high bandwidth, which is interesting for the people over here. Bandwidth is always good.
What's the scale? Is this hundreds of meters or?
I have to admit, I have no idea. I just asked our software guys to send me a screenshot. So
he asked what the scale of the map is, by the way.
Yeah, I know, but also I have to recount the question. Sorry.
Exactly. Good.
Okay, so I think we're pretty much through, and thanks.
So if you leave the room, please use the door in the front on the right side, take all your trash with you, or wait for the next talk, which is about security visualization on a correlation engine.
If you don't need to get your rover to the moon, you can get at least this way, at least somewhere.
Yeah.
So,
and for those that are in the audience, we will now, lift this cover. And unfortunately, please do not put it on the stream, because we do not want to have it in the internet yet. But, voila, there it is.